Now we will talk about the advanced topic in the supersymmetry beyond the phenomenological point of view. We will start some how can we construct some supersymmetric Lagrangians in the presences of the basic principle like as the holomorphy, and we will turn to the possible constructions, for example, the supersymmetric QCD. First of all, we will restrict our supersymmetric theory as unequal one. So there's only the one supercharges, and we constrains the condition of the holomorphy for the superpotential. So the Lagrangians only depends on the Kara-Schiffer fields, and there are no dependence on their Hermitian conjugate field. This imposes a very strong constraints on the supersymmetric theory. So the general supersymmetric action can be written by the several pieces for solve the potential, which is the functions of the both the Kara-Schiffer fields and its conjugate, but the holomorphic superpotentials and the gaze kinetic functions as coefficients of the superfield strengths, the holomorphic of the Kara-Schiffer field, so there are no dependence of the conjugates, and this gives a very strong constraint. For example, the holomorphy functions can provide the following superpotential form. This is a simple one if we consider only one example. Then this is the superpotential. We assume that the renormalizable one. The superpotential has the mass dimension of the 3, so the Celtic powers the eigenvalues here, and also the burst orders eigenvalues because this is just a third pole contribution. And in the point of view of the holomorphic function, both the mass and the coupling wise can be treated as the Spurian field, and they also cannot depend on the complex conjugate, so there will be no m star and the y star. And such holomorphic constraints will give the very powerful restriction when we ask the quantum correction, because there will be no additional loop corrections. This can be generalized by the non-renormalization theorem already we discussed before. If the supersymmetric Lagrangians satisfy the holomorphy, then there will be no additional correction from the perturbation theory. More precisely, this can be stated as the if the three levels potentials exist and the effective potential takes the form as the contributions from the three levels one, and the other ones come from the non-perturbative effects, and there will be no effects from the perturbation contribution. The example of such a non-perturbative effects instanton or strong gauge dynamics, QCD. The essential visions for this non-renormalization theorem of the supersymmetrics comes from the superspace integral with the Grassmann variable. The superpotentials appears only through the Kara superspace integrals. So there are only these k zeta, no zeta bar integrations, which is coming from the term definition. But when we do the perturbation theory in the superspace over the x and the zeta and zeta bar, the loop diagram shows integrals over the full superspace coordinate for the Grassmann variables of the zeta and zeta bar. So the loop corrections in the perturbation theories arise when it takes the form of the full superspace integral like the d for zeta, which is contained two variables zeta and zeta bar. Which is that this forms appears when the supersymmetric Lagrangians given by the color potential, and so the such a holomorphic potential cannot contribute the perturbative loop correction, but the renormalizations appears for the kinetic term and the wave functions of the field. So, for example, the color potential, it gets the perturbations effects from the loop, while the potentials are still changes. Now we can construct the effective superpotential by considering this non-renormalization theorem. We can use the various constraints from the symmetry, like as the R parity or holomorphy and the dimension analysis and the renormalization requirement. The effective potential should remain holomorphic property. So the coupling constant will treat the coupling constant as a Spurian field, and this can now also depends on their complex conjugate. And we can impose the global symmetry for the supersymmetric theory by assigning the R charges for each color superfield, and the potential must transform under this R symmetry. So, for example, we can assign the R charges for each term. The superpotential should carry the R charges of the 2 because there is the minus 2 for the superspace integral. And finally, the dimensional analysis can provide some restriction. The superpotential has a mass dimension of the 3 by considering the mass dimension of the Grassmann variable. So by combining these constraints, the holomorphy symmetry and the dimensional analysis restricts the possible form of the effective superpotential and the additional contributions of the loops that does not exist by the non-renormalization theorem. So we can determine the unique superpotentials for each gauge theory. But additionally, the wave function and the gauge coupling can be renormalized, unlike the coupling. For the gauge kinetic term as coefficient of the superfield strength, this is denoted by the f of the pi I, and f also should be the holomorphic functions of the Kähler superfield. For a simple gauge theory, this is given by the constant gauge coupling, so the gauge kinetic functions are just given by the constant parameter. And we can expand this superfield strength to the component field. Then the usual gauge kinetic terms appear. The first term corresponds to the field strength, and the second term corresponds to the theta term with the dual f tilde. But we can combine these two terms. And also there will be the additional gauge in the kinetic term with lambda with the gamma matrix. We can combine the field strength and the theta term by defining the complex gauge coupling tau. So now the theta terms appears as the real part, and the original kinetic terms appears as the imaginary part. Then the gauge kinetic term can be written as the one single complex parameters, which is to behave as holomorphic quantities for this supersymmetric theory. But this holomorphic gauge coupling, tau will learn over the renormalizations. In particular, the perturbation corrections, the holomorphic gauge coupling only occurs at the one loop. And higher loop corrections can generally involve with the non-holomorphic dependence on the coupling. So the such high loop corrections will not appear in the holomorphic Lagrangian. So the learning behavior of the holomorphic gauge coupling tau can be exactly determined with the following form, with only the one loop effect. This is the learning coupling with the logarithm. B0 is determined by the mathematical components of the theory, which correspond to the beta function coefficient. So for the unequal one gauge theory, we can determine these beta functions by using the representations or assigning the group for the mathematical superfield. So this is the quadratic Casimir slopes as joint representation, and the TR is the correspond to the Dinkin index of the space representation. So this is similar to the QCD and the Yang-Mills theory. So we introduced the holomorphic gauge coupling tau, but the coupling can be defined through with the physical one. The Wilsonian actions or Lagrangian, the kinetic term of the matter field, not the gauge field, generally take the form of the color potential pi dagger pi, and this is a non-holonomic. So the coefficients of this kinetic term of the matter color field has the renormalizations because it's non-holonomic. So the coefficients that wave function normalizations are here. So we should rescale the Kalash-Pop field. This is the same with the quantum field theory. And this rescaling changes the past integral measures and the factor receives the gauge kinetic term. So the due to the changes of the wave function normalizations of this Kalash-Pop field coming from the non-holomorphic, so the gauge kinetic term also shift. And this is called the physical gauge coupling. So there are two results. First of all, we already discussed that the holomorphic gauge coupling tau receives the correction from the one loop, but the physical gauge coupling also obtains the rescaling of the field by this wave function normalizations coefficient z. The difference between these two couplings arises from this wave renormalization factor z. And these epochs can be received, and the learning of the physical gauge coupling receives additional contributions from the anomalous dimensions of the matter field. So we can systematically find the difference between the holomorphic coupling and the physical coupling, and the difference will involve with the logarithms of the wave function normalizations, which can be also defined by the anomalous dimension small gamma of the matter field. So originally the beta function coefficients determine the fundamental quantities of the group theory, but there are additional contributions from the anomalous dimensions of the matter field. So by using this part, we can obtain the exact beta function, also called the NSVZ beta function. So the beta functions of the gauge couplings now contains the fundamental quantities of the group theory and the anomalous dimension, and there will be the additional contributions from the denominator, which comes from the canonically normalized physical gauge coupling. And this formula is exact for all the perturbed types and all loops through order. And all information of the higher order collections are encoded in this closed expression. This is a very strong constraint for the supersymmetric theory. And by using this NSVZ beta function, we can obtain the complex expression for the RG flow, and this will give the exact results of the supersymmetric quantum field theory. So today we discussed the holomorphic theory, and this can constrain the quantum fraction very strongly. Such a holomorphic structures of supersymmetric Lagrangians can provide the non-renormalization theorem, and as we just only the tree-level and non-perturbative epochs are important. But the case of the color potential, it modifies the wave function renormalizations and makes the rescaling of the superfield. And we turn to the how can we construct a supersymmetric gauge theory. We can combine the gauge coupling and the theta term into the single complex parameters, and the holomorphic strongly constrain the learning of this coupling, and we can add the additional epochs from the canonical renormalizations of the field. By defining the physical gauge coupling, these two contributions can be expressed by the anomalous dimensions of the matter field. So taking these all the epochs, then we can obtain exact NSVZ beta function for the gauge coupling. So we discussed the holomorphy and how this can constrain the supersymmetric theory. And continuing that, we will turn to the supersymmetric QCD. How can these epochs really operate in the realistic theory.